Hello and welcome to my new video. This will be the first video of my new playlist about 3D modeling and chemistry. So I will demonstrate various possibilities of applying 3D modeling, script-based 3D modeling for chemistry. And in this first video, we will speak about atoms, how to, of course, this is the start, how to model an atom. And the problem is, of course, that first we have to think about what is an atom, can we see it at all, and how should we visualize it? Should we visualize it at all? So in the back, you already see a visualization of an atom. This might be a boron or a carbon atom. And yeah, I will speak about first what this means, what is the reality behind this model, and second, how we can build such a model. And as always, I will give links and links to my GitHub account as well in the comment section to this video. In my GitHub account, there will be various scripts for the most important models I will be showing in this video. The first thing we have to talk about when talking about visualizing atoms is the question, can you see atoms at all, or to which extent can you see them, or which things do we have to ignore if we want to visualize them? And I want to discuss this question here with this very schematic atom. It's a very simple atom, the most simple one. It's a hydrogen atom. It's a nucleus, positive charged nucleus consisting only of one proton, and surrounding the nucleus there is this electron shell, which in the case of hydrogen it only contains one electron, negatively charged electron. And the first problem when trying to visualize it or trying to see it is that atoms are smaller than the wavelength of light. So that means with light, it's not possible to visualize it or to see it because everything that is smaller than the wavelength of light will not be correctly represented by light. That would be the first problem. The second problem is that the constituents of the atom, so nucleus and the electron, are very, very small, even much smaller than the atom itself. So even if this atom would have, if we could enlarge it to a diameter of 10 centimeters, the nuclei still would be less than 10 micrometers. And this means they still would be smaller than a usual bacterium. And we cannot see a bacterium, so we cannot see a nucleus of an atom, even if we would enlarge the whole atom to 10 centimeters diameter. And the third problem when visualizing atoms is that they are not they are so small that wave-particle duality applies, and it means that the constituents of atoms do not behave like we are accustomed to from macroscopic objects. I will speak about this in the next slide. So this is a classical experiment where you can demonstrate the wave-particle duality. Assume you have an electron beam and you let it hit a two-slit, and behind this two-slit there's a screen which is capturing the electrons and lighting up where the electron have hit. And in case the electron beam would consist of particles, this is what you would get. You would get a more or less perfect image of the two-slit on the screen behind this two-slit, because either an electron would go by the left slit and then it would hit the screen, or it would go by the right slit and then would hit the screen on the respective place. But that's not what you get. You get rather a very strange image. You get a pattern like this, similar to this. And this is the result from a typical wave. So if a wave is hitting the two slits, then two new waves are emanating from each of these slits, and these waves are interfering with each other, and they are then this interference then is producing this pattern which you see there. And that's precisely the pattern you will observe with the electron beam on one hand. On the other hand, however, you can see that these are nevertheless individual electrons because they are hitting the screen on individual places. So it's electron beams have kind of both um, properties, wave properties and particle properties. And that is difficult to understand with our brain, which comes from a world where it's not possible to have both properties, and that's the main problem when looking at atomic or atoms or atom envelopes to understand what you are seeing. So, as kind of a summary, you can say the location of the impact of the electron on the screen is determined by the wave character of the beam. Actually, the probability to find an electron at a given position, this is determined by the wave character. This is precisely the wave character of the beam. When we go back to our hydrogen atom, which has a one electron in its envelope, then for this envelope as well, there is a particle wave duality. So this is a particle, but it's also a wave. And this wave, again, is determining the probability to find this electron, to encounter this electron at a given position. And um, we can represent this probability by this dot cloud as I have done here. So the denser the dot cloud, the higher is the probability to find this electron. So this is not that this is a cloud of 6,000 electrons here. These are 6,000 elements. And by the way, the electron is much smaller than a single dot of this cloud. But this would be a picture you would obtain if you measure the location of 6,000 different hydrogen atoms, and each time you measure the location of the electron, and then you super compose it, you combine all these measurements in one picture, and then you would obtain a picture like the one here. So with a very low probability to encounter the electron at the edge of this envelope, and a higher probability to encounter it when you go further towards the nucleus. Before I continue to speak about the physical and chemical meaning of this dot cloud, want to speak about how to visualize such a dot cloud, how to produce it by script-based 3D modeling. And I will, so we have to do two tasks here. One task is to distribute elements on a spherical surface. I will talk about this first. And the second task is to distribute elements, let's say, for example, along the x-axis. So from the center with a high density of dots towards the periphery with a low density of dots. We will use random numbers from periphery for both tasks. And I will start now with the first task with distributing elements on a spherical surface. And I have to admit, so I have done this before in videos before about polar distributions. I produced a video, but I have to admit that I did a mistake in these videos, because when you randomly distribute elements along latitudes and longitudes on such a sphere, as I've done in these videos, you will not obtain an even distribution. You will have an accumulation of elements versus the poles of your sphere. As you can see here the poles are located on the x-axis, and you see that elements there are accumulating. And this is something we do not want in our case. We obtain our even distribution on a spherical surface by distributing elements on the surface of a cylinder where the sphere is inscribed. So we have a sphere of a radius r and a cylinder surrounding the sphere, and we just distribute our elements on top of the cylinder, and then we project the elements down to the sphere. And this would generate an even distribution of elements. In reality, we will do it a bit different. We start with the point on the x-axis in the distance r from the origin. and then we rotate them by an angle alpha around the z-axis. And this angle alpha is calculated by arc cosine of h divided by r. And the value of h again is generated by random numbers. And then we have to rotate these elements randomly around the x-axis as a last step. And then we have a distribution like this. Um, I will I will include a respective script for such a distribution in my GitHub account. So in case my explanation here was a bit too short or too confusing, just have a look at this script, and then I think it's not very difficult actually. Okay, this enables us to really do an even distribution of elements on this spherical surface, but this is only one step. As a next step, as another step, we also need a distribution along, let's say, the x-axis in such a case. We don't want to have a spherical area. We want to have this cloud dot I showed you in the beginning. And to obtain this, it's a good opportunity to speak about random numbers in more general. First of all, Porphyry is producing random numbers between 0 and 1, and I think many other programs will do it in a similar way. And I want to shortly discuss how it's possible to transform such random numbers. So, as a very simple case, just imagine you want these random numbers, but you want to have them in another range of applications. So we have got 4 numbers here produced by Porphyry, and we want to have them from 0.2 to 2.2, not from 0 to 1. And what you would need here, of course, is a linear transformation. So you multiply these numbers by 2 and then add 0.2 to each of these numbers, and then you will have this transformation, a linear transformation, and they will fit into your new range of application. So now I'm replacing these 4 random numbers produced by Porphyry by a large number of random numbers, such a cloud of random numbers. And again, with this random transformation, with this linear transformation, you won't see much difference. So it's the same distribution of random cloud-like points before and after the transformation. But you can change this by using nonlinear transformations, like, for example, this x to the power of 2, this quadratic equation. In this case, you will get a new distribution of random numbers where you will have an accumulation of random numbers at the bottom of your new range of application. If you use the inverse function of square x, like the root of x, then you will have this accumulation of numbers on top of your new range of application. And what is also possible is to have an accumulation of random numbers in the very center of your range of application. Yeah, I cannot ask you, but ask yourself, how would you do it? Which kind of transformation could you use? It's a equation by the power to the power of 3. So it's this equation here, which you could use. And I just want to shortly talk about the parameters you can use to adapt this equation to your specific problem. Parameter A will spread or constrict your equation, your transformation. Parameter B will shift the position of the transformation with respect to the x-axis, and the parameter C will shift your equation with respect to the y-axis. So you can apply these parameters and obtain whichever transformation you want. Here I have used 2 different kind of transformations for distributing the elements of this dot cloud along the x-axis before doing this spherical distribution I have shown you in the beginning. And you see I've used a linear transformation and I have used a quadratic transformation, you see that the difference is not too big. It's only really a minor difference, surprisingly, I have to say. So in reality, the probability of encountering an electron is decreasing exponentially from the nucleus to the outside. And in order to somehow simulate this, I think the quadratic transformation is more suitable than the linear transformation. So I'm using this quadratic transformation in our case. In the first part of this video, I've been talking about how to visualize an atom. And visualizing an atom basically means visualizing the electron envelope of an atom. And I've been talking about how problematic this is, as you cannot see the electron, and it has this wave-particle duality and so on. I've been talking about that these dot clouds you can see in the background are somehow representing waves of probability. So the probability to encounter the electron at a given place, and this is has different densities around the atom. Okay, that was and that the electron somehow is forming a standing wave around the nucleus in an atom. In the second part, we will talk about what happens when we add some energy to the system. So now we have an electron around a nucleus, and now we add some energy to the electron. Um, Basically, the electron has to go further apart from the atom nucleus, because the farther the electron is apart, the more energy does it take. The electron has a negative charge, the nucleus a positive charge. Now the bigger the distance between electron and nucleus, the more energy is there. But this is more complicated than just like this, as you will see. Before speaking really about what is happening when we excite our atom, when we add energy to our electron envelope, I just want to shortly mention one small convention that I will do in future pictures. I will only show a section of this dot cloud, because it can become in some cases too confusing if I'm showing the whole dot cloud. So I will use this box here for sectioning my dot cloud, and will only show the dots which are inside this box in the XY plane. And in the case of this simple ground state, 1s orbit, so we call it orbits, these dot clouds, this will not look much different from the whole picture, but in the other cases it will look quite different, and it will give you a clearer impression. Now we are starting to talk about what is happening when you add some energy to an atom, or better to say, energy to the envelope of an atom, to the electron of an atom. And actually, the electron will behave very strangely. And just to show you how strange it is behaving, I will show you first this example from classical physics. So in normal life, what is happening when you add energy to a given system? So here we've got a beaker of water and a flame below. So you add heat energy to this beaker, and of course the water will warm up, and the more heat you add, the more the water will warm up, so the temperature will rise. When we add energy to the envelope of an atom, to the electron around an atom, it's not the temperature that will rise, it is rather the distance from the nucleus. I already told that the further apart the electron is from the nucleus, the more energy the whole system is containing, since the negatively charged electron and the positively charged nucleus will attract each other. Now, when we increase the energy we add to the electron envelope of an atom, will just the distance to the nucleus increase of this electron cloud, or of this cloud of probability? This is not the case. It will rather happen something similar to this red curve, which is very schematic here. So it's not representing the real steps which the electron will take, but you see it is a step-like process. So when you increase the energy you add from 0 to a certain amount, first nothing will happen. So the electron will not accept the energy until you reach a certain level, a certain value, and then the electron will accept this energy and will take up energy. We will see what happens to the electron in this case very soon. And then if you add more energy again, nothing will happen. The electron will not accept this extra amount of energy until you reach another threshold or another level, where again the electron is prepared to take up this energy. So this is very different from what you observe in real life. And the state where the electron has not accepted any energy so far, so the state with the lowest amount of energy of the electron, this is called the ground state. And all the other states where the electron has accepted a certain amount of energy, these are called excited states. Here you see the distribution of probability to encounter an electron close to the atomic nucleus for the ground state and for the excited state, for the first excited state. And you see, on the one hand, it's true. So the distance of this cloud of probabilities is larger in the case of the excited state than in the case of the ground state. So this is the reason why there's more energy in the excited state, because the electron is further apart from the nucleus. But on the other hand, you see this is not the only difference between the two states. The distribution of probabilities looks pretty much different in the excited state from the ground state. So there's more to it than only this difference in distance to the nucleus. And this difference becomes even more obvious when you look at the second excited state. This would be the 2p orbital. By the way, we are calling these states orbitals. So the ground state is the 1s orbital. The first excited state would be the 2s orbital, and the second excited state now here is the 2p orbital, in this case the 2py orbital, because these orbitals are centered around the y-axis. And this is even a bit more, has a bit more energy than the 2s orbital. I could now show you I could have produced visualizations of all orbitals. There are quite a number of orbitals, and they look interesting and beautiful, but yeah, I think you can you can have a look at this if you're interested in how these orbitals look. If you look at Wikipedia, you find interesting and nice visualizations of such orbitals. What I want to show you now is an overview about orbitals which exist and about their energies. So here I have collected the orbitals and arranged them according to increasing energy from bottom to top. So on the very bottom we have the 1s orbital, the ground state, the lowest energy, and then energy towards the top is increasing. And you see there is a large number of different orbitals, and this is even not enough. There are more orbitals than the ones I have collected here. The ones I have shown you so far are the 1s orbital. They are labeled in red color, the 2s orbital and the 2p orbital. And there are two other orbitals, the 2px and the 2pz orbital, which are then centered around the x-axis and the z-axis. Let's have a short look how these orbitals are organized. So every dash corresponds to one orbital. And first of all, there are several shells around any atom. These shells are represented by the numbers. So that's shell 1, shell 2, shell 3. And each shell contains the number of orbitals in each shell are to the power of the number of the shell. So shell 1 contains 1 orbital, shell 2 contains 2 multiplied by 2, 4 orbitals. Shell 3 contains 3 multiplied by 3, so 9 orbitals, and so on. So shell 4 already contains orbitals which are not shown here. We have already talked about this. The electron can only be excited by specific amounts of energy, and this amount of energies, they have to correspond precisely to the distance between the orbitals here in this scheme of orbital energies. So I have shown you that if you want to lift the electron from the 1s state to the 2s state, you have precisely to add the amount of energy symbolized or marked by this arrow here. And usually this energy is added by a ray of light or by a photon, and the energy of this photon has to fit precisely to this energy which is needed here. And the same is true for all the other transitions between all other states here in this scheme. Now let's talk about orbitals of other elements, not of hydrogen, but of other elements. And the problem with other elements is that it's much more difficult to exactly calculate these orbitals and their energy. But you can use some measures of approximation. And when you do this, you end up with pretty similar orbitals as in the case of hydrogen. So I have taken the same scheme as in the case of hydrogen. And now we can ask, how are these orbitals occupied? Then other elements have not only one electron, but more electrons. And there are two rules which we have to apply for this filling up the orbitals. And that is, first of all, you have to fill them up from bottom to top. So the orbital of lowest energy is occupied first. And second, you can have two electrons in one orbital. So each electron is occupied by two electrons. If you apply these rules for the first three periods of the periodic system, you end up with a table like this. So I will go through it with you. Let's have a look at the 1s orbital. As we already said, hydrogen has one electron in the 1s orbital. The second element, which has two electrons, then is helium, and then the 1s orbital is filled. So the next two elements will fill up the 2s orbital, so lithium and beryllium. With beryllium, we have four electrons, and this will fill up the 2s orbital. And then the next orbitals are the 2p orbitals. There's place for six electrons here. So the next six chemical elements will fill up these 2p orbitals: bore, carbon, nitrogen, oxygen, fluor, and neon, and so on. The same is true then for the third period. So it's actually pretty simple to fill up these orbitals. Why is this important? Well, this is important because the position in the scheme of a given element determines pretty much the chemical characteristics of this element. And this is due to the fact that if a shell is, an outer shell is completely filled or is completely stable, then this configuration will be pretty stable. And this is then called the noble gas configuration, or also the octet rule, because then this element has 8 outer electrons. So therefore it's the octet rule. Although it's not always an octet rule, but well, we can live with this. So I will give you some examples. For example, if you look at the noble gases, argon, neon, and helium, they all have completely filled outer shells. Helium has filled the 1s orbital. In the case of neon, the 2p orbitals are filled, so the second shell is completely filled. In the case of argon, the 3p orbitals are filled, and it's not precisely the third shell which is filled up, but the 3s and the 3p together. This is an octet again, and this is a particularly stable configuration, and therefore these noble gases won't react or will not react easily with other elements. They are satisfied. They don't want other electrons or further electrons in their shells, and they don't want to lose electrons as well. So they will not do many chemical reactions. It's completely different if you look at things like sodium and lithium and hydrogen. These are all elements which have one electron in the s orbital, only one, and they have the tendency to lose this electron. Then they have an empty outer shell, and this is, as I said, particularly stable. So they will try to get rid of their lonely electron in the outer shell, and then they are positively charged with one positive charge. If you look at magnesium and beryllium, it's similar. They have two outer electrons, and they also want to get rid of these two outer electrons. So then they have two positive charges. It's the other way around with chlorine and fluorine. Those elements have 7 electrons in their outer shells, and they clearly want to have 8 electrons. So they try to pick up electrons from the outside world, and then chlorine and fluorine, they both are negative, have one negative charge. And it's similar with sulfur and oxygen. They are lacking 2 electrons to reach the noble gas configuration. So they try to pick up 2 electrons from outside, and then they have 2 negative charges. For the end of this video, I want to give you something like a picture from a real physical world, from the world we know in our daily life. And that is that you can compare the wave of probability surrounding an atomic nucleus, like a standing wave, with the vibration of a string of a guitar. And I have shown you there is in the case of the electron envelope, you have this ground state and the excited states. And in a similar way, in a guitar string, you have this basic vibration and you have overtones. And again, as in the case of the electron envelope, you have very specific overtones. It's not that you can reach every kind of tone, but only very specific overtones. Again, as in the case of the electron envelope, where you only can address very specific orbits, very specific states of energy are possible, not all states. Okay, this is something like an analogy. In the next video, we will speak about what happens when you combine several atoms. So when you combine the orbits of several atoms together, and how you can combine them and then bind these atoms together and produce molecules from these atoms. Up to then, it will take some time.